Hi everyone, and welcome to the video that's going to be going over geometries. If you have no idea how to do a Lewis structure, please stop this video at this point and go back to the video where we go over how to create a Lewis structure, because we need them. So before we get started, I just want to tell you a few things. We're going to go over some basics, and then I'll show you a tool that I like to use a lot in my classroom. And then from there, I'll actually show you a model or two so that you can understand the three-dimensional shapes of what a geometry is. So to break it down before we even go ahead and start into those things, when you create a Lewis structure, you are drawing this on a piece of paper, right? Which is a two-dimensional object. And so when we go from a Lewis structure to a geometry, we want to take our two-dimensional object and make it three-dimensional while drawing it on a 2D piece of paper. So stay with us. We'll make it easy, we'll make it straightforward, and here we go. Alright, when we think about what a geometry is, there are technically two different types of geometries we can refer to. And at first it might not seem very straightforward, but as you hang on for a little bit, we'll go into what the difference between the two are quite quickly. So the first one that's listed on your screen is the electronic geometry. When you're looking at the electronic geometry, it's really the 3D look at the molecule that you just did as a Lewis structure. And when we talk about electronic, we're actually considering where the lone pairs or electrons are. When we look at a molecular geometry, also known as a molecular shape, we only care where the atoms are. So let me give you an example of this that we've already looked at when we did our Lewis structures. So here are two resonance structures of SO2, and you can see here on both structures that the S in the middle has not only bonds, but it also has these two dots or electrons above it. When we're looking at the electronic geometry, we're going to care about all of the lone pairs that are on this structure, whereas with the molecular geometry, we only care about the sulfur and the two oxygens that are connected, and that's what we'll be able to draw. So showing you a little bit more of the notes, there's a few things we need to take into account before we go into the rest. When we're drawing a geometry, what we are referring to is drawing the molecular geometry, not the electronic geometry. So a couple things to keep in mind. Since the molecular geometry only cares about where the atoms are, we are not going to draw any of the lone pairs or the dots that we had on our Lewis structures. The second part is that every single bond, whether it's single, double, or triple, will only be shown as a line, a wedge, or a dash. And you can see either above or below what these mean. So when we draw a line, it means that the bond is actually in the plane. And I'll elaborate further on that. When we have a wedge, it means it's coming out towards you or off of the paper that you're drawing your molecule on. And opposite of this, the dashes are going to mean that it's going behind the paper or backwards. There are 11 molecular geometries altogether. And when we talk about electronic geometries, there are only 5. And I'll show you a tool that I use in my classroom, as I mentioned before, where you can easily depict which one you want to use for your structure that's given. Here are the rest of the notes. So we're at this point here. 5 of your molecular geometries, or 5 of the 11, all the bonds are going to be a straight line and are planar. What this means is that every single atom will go ahead and touch one plane. And it will show you this using one of the 5 that are listed here below. So the 5 that are planar and only get straight lines would be linear, bent, trigonal planar, T-shaped, and square planar. With that being said, there are 6 additional geometries that aren't mentioned on that previous list. And these 6 are going to be three-dimensional, meaning that not every single atom will lay on one plane. Because not everything sits on a 2D surface or a plane, some of the bonds will have to be looking like they're coming out towards you or behind your paper. So all of the geometries of these 6 will include A straight line, which means that it's in plane. A wedge, which means it's coming forward towards you, and dashes that go backwards. And those 6 you can see in this list here. And so just in case if you haven't heard these, let's go through this list. Number 1 is tetrahedral. Number 2 is trigonal pyramidal. Number 3 is trigonal bipyramidal. 4 is seesaw. 5 is octahedral. And 6 is square pyramidal. So a few things to keep in mind, and they're starred right here, is that everything, whether it's an atom or if it's a lone pair, everything wants to be as far apart as possible. And so that's the whole reason why we have these different 3D shapes that we get from our Lewis structures. So if everything wants to be as far apart as possible, they're going to move to accommodate that. The second thing that we have to keep in mind is down here. If we're going to use a wedge, we have to use a dash, or vice versa. If you want to use a dash, you have to use a wedge. They come as a pair, and you cannot have one without the other. So here on your screen is one of the models I have, and we're actually looking at trigonal planar, which if you refer back to the list that we just had, this would be considered one of the planar geometries that we have. And so I'm going to rotate this in a second so you actually can see what we're talking about. And I really hope I haven't scared you off yet by saying planes and such, because it's quite simple. So if I go ahead and rotate this to where you can go ahead and see its side, I hope that you would agree with me that every single thing seems to kind of line up in a straight line when it's turned this way. And so the easiest way that I can show you on this video is if I put my hand here, which I normally do use my hand in my classes to show a plane, or a piece of paper works well too. If I were to set this molecule onto my hand or my plane, every single one of these 4 atoms would touch it, which means they all lie on one plane, and so that means that every single one of these bonds would have a straight line. So here on your screen now is tetrahedral. So unlike the last one you just saw, tetrahedral is now on the list that has to use a wedge and a dash because it's 3-dimensional, which also means that all of these atoms cannot lay flat on one plane. And so I'm going to rotate this up a little bit and start rotating it around, so hopefully you can actually see how they're not all flat. So just rotating that up, hopefully if I go slow enough, you guys can see that the 3 at the bottom are angled downwards. Okay? And so eventually what we're going to want to do when we're playing with these models, or practicing, should I say, is that you want to align things in which you can get the most atoms on one plane while also getting one wedge and one dash. And so you're going to see also that there are 2 different geometries where it's acceptable to have 2 wedges and 2 dashes, but only 2 of the 6 that's acceptable for. So with a little bit of practice, I'm going to rotate the tetrahedral model this way. And what that's going to allow me to do is to place the top white sphere, this left side sphere, and the middle black sphere all on the palm of my hand or in one plane, which hopefully you can see right there. And if I rotate my plane a little bit, hopefully you can also tell that this sphere is coming out towards you or forwards. And if I go ahead and continue that plane, we're actually hiding that one that's going backwards or behind the plane. So when we are going to draw tetrahedral, the top, the middle, and the side here will all have straight lines connecting them. The atom that's coming out towards you would have a wedge, and the atom that's going behind the plane would then be a dash. So let's go ahead and try those things out. On your screen now is the trigonal planar, which is the model that we did first. And we said that all of these atoms would go ahead and touch one singular plane. Therefore, every single connection that we have between the middle to the exterior or outermost atoms would be a straight line. When we look at tetrahedral, we said that that would not be the case, and so we'd have to line some up that would all be on a plane, and then we'd have one wedge and one dash. And so if I try to orient that how we see in the image here, the top, the middle, and the side, those are the ones that we said were going to be straight. And this atom that's coming out towards you would be your wedge. And then the one that's going behind that you almost cannot see would be your dashes. So how do you know what your Lewis structure is going to turn into? I have a 2-page tool that I like to use, and this is the first page. And when you're looking at your Lewis structure, you're going to be concerned with the 2 columns here in the middle. Actually, I'm going to point up to him up here. So bonding domains, every single bond, whether it's single, double, or triple, is going to count as one bonding domain. I like to call these also as bonding areas. That sometimes helps people also remember that a triple bond still only counts as one, as does a double bond. Non-bonding domains. These are your lone pairs. Every lone pair, or 2 dots, counts as one non-bonding domain. Again, you can think of these as areas, so you normally typically draw your electrons together in pairs, so that would count as 1. So let's go ahead and practice this. But before I do, I'm going to go ahead and show this paper. You can pause and take a screenshot of it. For those that are in my class, you will have this document at your disposal. And here is the other page that you might need. So go ahead and pause for both of those, take a screenshot, or make sure you have this resource at your disposal because we will be referring back to it. Something that you need to also take note of is that when we're looking at this column here, which is our molecular geometries, this darker line is going to be your wedge, and the lighter line is actually your dashes that are going behind. And you can see this also because the sphere is bigger on the wedge and smaller on your dash. So it actually shows you how to go ahead and draw your geometries on this resource. So let's go ahead and look at our SO2 that we had before. Whenever we're using that tool and talking about bonding versus non-bonding domains, we only want to look at the center atom. So let's go ahead and get that down. So I put a little bit extra here, but on the right-hand side, you can see we only care about the center atom. If you don't have a center atom, then your geometry will be linear. On the left-hand side, I actually want to figure out how many bonding and non-bonding domains my center atom has, which is our sulfur. Remember that for bonding, no matter whether you have a single, double, or triple bond, they count as 1. So if we look at the molecule on the left, we have 1 bonding domain on the left and 1 bonding domain on the right, therefore giving us 2 bonding domains. As far as non-bonding goes, remember it counts as a pair for 1. So we have a pair of electrons, we have a pair of electrons up here, which counts as 1 non-bonding domain, and that's the only pair of electrons we have. So we have 2 bonding and 1 non-bonding domain. So then we can pull out that tool that we just went over. We can actually find this on our first page. So moving that up a little bit, our bonding domains was 2, and our non-bonding domains was 1. And so what that means is that our molecular shape or our molecular geometry is going to be bent. And bent is a planar geometry, so no wedges and no dashes. But we also can look over to the left-hand side, and we don't have anything in this box, but that's because it refers back up to what's right above it. So we only are actually having the electronic geometry written down once, but it applies to every single box until you see another electronic geometry. So alright everyone, you have everything you need to be successful to do a Lewis structure to geometry transition, going from your 2D Lewis structure to your 3D geometries. The next step, and of course there's always another step, is to figure out is your molecule polar or not. So tune into the next video and we'll see how that's done.